lost me.
The very beginning.
So I just acknowledged my two co-authors, Valentina Breschi and Alessandro Chiuso, whose contributions to this work was actually fundamental to get to this result. So the focus on the work is on data-driven control. And for those of you who are not familiar with this terminology, with data-driven control, I intend all those techniques who focus on control design, but actually without undertaking first a full modeling study of the plant. So the plant is assumed to be unknown, and we have a set of data, one or more sets of data available for taken from the plant, but we don't want to identify the plant. We would like to map the data directly onto some control action. This is motivated by the fact that modeling, so considering either physical modeling and system identification, usually takes most of the time devoted to a control project. It was estimated that it is approximately 75% of the total time. So it is one of the most, let's say, expensive and time-consuming tasks within a control project. And this is also witnessed by the fact that the number of publications on data-driven control has grown significantly over the years. You see here on the left, the plot shows the number of publications that has increased starting from 2010 until today in the past years. And on the right-hand side, you see a plot that shows just the publications devoted to predictive control, so data-driven predictive control. And you see that there is a growing interest prompted by the fact that data are more and more available in many applications, due also to the computational power available to many devices and to the recently introduced techniques within the field. So in my presentation, I will talk about predictive control, and in particular, I will start by introducing the data-driven predictive control that already exists, that was actually
It seems that we lost Simone again.
Bonjour Xavier.
Xavier, your mic is off.
Bonjour Charles.
Et désolé pour le retard. Hein.
Ah non, non, quand même, on n'a pas encore commencé puisque.
Oh, Simone is back.
I hope,
on a commencé deux fois.
I hope it's not going to be like that.
Can you not connect your computer to the network via cable? Are you on the Wi-Fi? Oh, it's not easy.
Now it's moving.
So let me switch to a stronger connection, hopefully, because it's snowing right now. So I don't know whether this is due to the weather, to the bad weather. I should have been given a stronger connection, let's say.
Often it works better if you have if you connect directly your computer to the box if you're at home or.
No, actually, I'm in a hotel. I'm in Hanover now.
Ah, yeah. Okay.
So that's why. I mean, I thought that the connection was better, but then I connected to my phone. Okay. So this should guarantee that. I mean, if the hotel has problems, it should be fine. So were you until here? So where did I lose you? Okay, this way. So this is the outline of the presentation. So we'll first introduce deterministic data-driven predictive control and show you some limitations of this technique in order to motivate its reformulation within a stochastic setting. So the shift from deterministic to stochastic data-driven predictive control will be the focus of this presentation, And why that? Why we are so interested into data-driven predictive control? Well, for those of you who don't know it, but I mean, I assume all of you know it. Predictive control is one of the most promising technologies for advanced controls due to its inherent capability of handling constraints and to approximate optimal control over a receding horizon. So this is why doing data-driven control within a receding horizon fashion is so appealing from a practical point of view. So our main assumption is that our system is a linear time invariant system with both process and measurement noise with some statistics. And we assume that we don't know anything about this system. So we don't know either the system matrices nor the statistics of the noise. We don't know anything. We just know that the system is linear in time invariant. And we assume that we are given a data set, so a set of input and output data, provided that the input signal is persistently exciting of a sufficient order, and we will discuss later on what does it mean from a mathematical point of view. And then we also assume that our control problem is actually a regulation problem where the set point is just a constant over the time. So, and this constant is assumed to be given. Now, since the system is stochastic, when you formulate a model predictive control problem with this setting, you have to formulate it by taking into account that you have a stochastic perturbation of your output. So one way to formulate the optimal cost could be to take the expected value of the tracking error of the output plus some penalty on the amplitude of the input. That could be taken as a weighted average of the input action over the prediction horizon. And of course, you see that here some of the problems arise in the data-driven framework. So for example, A, B, C, and D are not given. We don't have any information about the statistics of the noise, so we don't know how to take into account the noise. And moreover, we also need to cope with the initial conditions, because actually we assume that we are not measuring the state, we just measure the input and the output. So let's see each of these problems, how can be tackled within a data-driven control framework. So first of all, let's see what already exists. So we would like to describe the predictive model in a purely input-output framework, so without relying on state data. And we would like to express the initial conditions also using only input and output. So let's start from the existing theory. So assuming that we have this state space model, we know from the behavioral system theory that any state space model of this form in a linear setting can be expressed by within a different form. So basically, we could state that any trajectory of the system can be taken, can be equivalent to a linear combination of the data that we have already observed under the persistency of excitation assumption. And so we just need to change this coefficient alpha of t, and by changing alpha, we just change the corresponding trajectory of the system that we want to consider, and that trajectory will be compliant with the system dynamics. So since this is true, then we can take this expression as the system dynamics, and we could also do similar observation to express the initial condition. So we all know that the state can be expressed as the expression that is illustrated in the slide. So a to the power of rho, where rho is a certain constant, times the initial condition of x, plus some controllability matrix times the past record of input and output. So for a stable system, we know that provided that the rho is greater than or equal to n, where n is the state of the dimension of the state of the system, then we can actually make the record of input and output data correspond to the initial condition, at least as rho is large enough, I would say. The problem is then how to tune rho, and I will leave this problem here because we will address it later on in the presentation. But just to let you know that turning the MPC formulation into a data-driven setting is not I mean, there's no free lunch also here. So we substitute the previous relations into the predictive control problem. So we have the formulation of the control problem, which is basically a quadratic control cost, and then we substituted the system dynamics with the assumption, the form given by the Willems lemma, so given by the expression of the trajectories of the system as a linear combination of the observed data, and then we substitute the initial condition with the correspondence with the past data. So this is proven to be equivalent to the model-based problem. So if we optimize the problem formulation like this, we obtain a sequence of inputs that correspond, so it's exactly coincident with the input sequence that we would get from the corresponding model-based problem, provided that the rho is big enough. We can also add an additional constraint like the one highlighted in red, and this would also guarantee both stability and recursive feasibility for our formulation, because it would be equivalent to the terminal constraint in the model-based framework. So everything seems nice. The problem is, what happens when we add noise? So what happens when the data that we use to approximate the system dynamics using the expression given by the Willems lemma are generated according to a noisy system, so a system affected by both process noise and output noise? Well, actually, in the literature, the only case that has been treated extensively is the case with only measurement noise. So we will start from that framework. So we assume that the true system changes according to this law, where we don't have any process noise, but we have measurement noise on the output. And so the output that we obtain in the record, so in the data set, and that we use to approximate and to model the system dynamics is actually corrupted by unknown trajectory of V. So we start from the nominal formulation with the terminal constraint, and we know that this is guaranteed to have stability or recursive feasibility. Actually, if you have noise, you have this additional term. You need to add this additional term to Y bar that you see in the first constraint. And this additional term is basically a slack variable that we need to regularize in the cost. So we add both sigma of t in the constraint and the term lambda sigma times the norm of sigma in the cost, because like that we're sort of trying to model the impact of noise on the output. But this is not sufficient, because actually we would like this noise to really model let's say the system dynamic, but we would like not to overfit it. And so we need also to regularize alpha and to link the norm of alpha and the infinity norm of sigma through the very last constraint that you see in the slide. I won't enter into the let's say very technical details of this. I just would like to show you this new formulation accounting for measurement noise that holds only for noise that is assumed to be upper bounded. So we assume that we have a bound on the norm of the noise. And what I would like to highlight is the fact that in order to account for this bounded noise inside the formulation and still having practical stability and recursive feasibility, we need to tune additional knobs. For example, we have a lambda alpha, we have lambda sigma, we have epsilon bar, and all these terms are actually hard to tune, because we have no practical guidelines on how to tune it. Consider that this is not even an identification problem, so we cannot think of dividing the data set in two parts and use one for training and the other one for validation, because we could do cross-validation only with a closed loop experiment. That experiment would really validate the choice of lambda alpha and lambda sigma, and this is somehow undesirable, because doing closed loop validation means that we need to take some formulation, let's say take some selection of lambda alpha and lambda sigma, implement the MPC controller, and then let it run on the system, which could also be unsafe for a bad selection of the coefficient of the penalty term. One other way to handle noise instead of adding this slack variable is to use regularization of alpha, but now the regularization is designed differently. So we don't just penalize the two norm of alpha, we penalize the one norm, And then we also take the orthogonal projection of alpha onto the kernel of the initial condition and the future output. So we have a smart projection of alpha. And with this projection, we can actually prove that we shrink the norm of alpha, so that we select, let's say, the right trajectory in the data set that are useful for our purpose. And so we avoid overfitting while at the same time guaranteeing a good control performance. Also, in this case, we have some tuning problems because we are adding lambda 1 and lambda 2, which are tuning knobs, and whose effect is actually very significant in terms of performance of the MPC in closed loop. So their tuning is all but trivial. This is even more difficult, of course, if you add also process noise, because there's nothing that basically, no results that basically say how to handle such a process noise. And in this case, if the process noise is also stochastic and the measurement noise has a stochastic distribution, the theory is lacking a real approach on how to handle noise in this case. So we decided to take this framework, let's say this setting into account, and to go back to the origin to reformulate the data-driven MPC problem using system identification tools, and in particular, subspace identification tools. And what I would like to argue in this presentation is that actually this is key in order to not only find a suitable formulation of the predictive control problem in the stochastic setting, but it's also useful in terms of tuning of all these let's say regularization parameters that you need to account for noise and not overfit the training data. So let's first change the system expression. So we just make a change, which is nothing surprising. So we take the initial model and we write it in an innovation form, so that we know that actually the system dynamics now is expressed by A minus KC, and if K is the Kalman gain, then we know that its maximum eigenvalue has a magnitude lower than 1. In this case, we could actually rewrite the initial condition, but in this form, actually, the approximation of the initial condition with the past records of input and output turns out to be much better, because this holds only both for stable and unstable systems, because we know that A minus KC is actually a stable matrix, and then for a rho that is sufficiently large, this transient term vanishes for rho that tends to infinity. And so we could actually express x of t as a controllability matrix times the record of past data, and we make an error which is negligible as rho is selected as a large number. Of course, we need to take care of the trade-off in the choice of rho, because we know that if rho is large, of course, we have a small approximation error, but we would like also rho to be low due to computational and memory constraints. And moreover, we will see later that this rho is also connected to the estimation of some covariance matrices. So the variance of the estimation of x would be larger in case of rho large. So rho, for example, could be taken as a sort of model order within this setting, and we could think of tuning it using, again, system identification tools like standard criteria for model order selection in system identification, for example, the Akaike criterion, but many others could be used. And if you do that, then you fix the first degree of freedom that was critical in the previous case using system identification tools, and you can proceed, you can go on. So you take the Henkel matrices, you decompose the Henkel matrix into the past and future contribution, and then you can rewrite the future output sequence as we all know these results. So the controllability matrix times the estimation for the state, which is, let's say, well computed as we said before, plus the term, the observability matrix, I meant. So plus a term that takes the product between the Henkel matrix and the input sequence, plus a final term that depends on the future realization of the noise. And of course, if you want to take the best prediction of y, one way is to project this future future outputs onto the row span of the past data and the future sequence of U, so that basically the contribution of the noise could be seen as negligible as the number of data tends to infinity. And so we end up with a predictive model, so that the prediction of Y, so we call it Y hat over the prediction horizon, is just the controllability matrix times the past data, plus something that depends on the future realization of the input sequence, which is the unknown variable to optimize in an MPC fashion, plus something that is small as far as rho is suitably selected and ND, the number of data, is large enough. So we have the opportunity of defining or formulating and proving a theorem that is the equivalent of the Wilhelm's lemma within this stochastic setting. And this theorem tells us basically what is how we can approximate, or when we can approximate the system dynamics using data only if the input is persistently exciting. And this is the form that we end up with. So we have that basically Y hat is a linear combination of the future sequence of Y times this alpha star, and this alpha star is nothing more than the linear combination of the past input that produces the estimation of the state and the input. And within this framework, we can also simplify the control loss, because actually, when you take the expectation of Y minus the reference, you could actually decompose it in these two terms, and you can observe that the second term, which is the expectation of Y minus the expectation of Y, is independent from the input sequence U. And so in practice, what you could do is just to take the first term, because the second one is not affected by the outcome of the optimization of the MPC, and the first term is nothing more than the norm of the difference between the predicted output and the reference output. So the final formulation of the problem in the stochastic setting for the data-driven predictive control is the following. So we have just the minimization over the prediction horizon of the difference between the best predicted Y, which is the projection over the suitable space of the original expression of the future output, minus the reference, plus some norm of the input. And then we have a specific expression for alpha. So alpha is no longer an optimization variable. It's given by this expression, provided that the data are persistently excited. And the interesting fact is that this formulation that we derived starting from scratch is equivalent to the constraint version of the so-called subspace predictive control scheme, which was introduced beginning of 2000, so more than 20 years ago. So it was rather surprising for us, because there is a one-to-one connection, and it was the two methodologies were not connected before. But it was nice to see that using system identification tool, you can actually prove that this subspace predictive control is optimal, in a sense that it minimizes the projection error and the effect of noise on the data. You could also show, if you look at the current version of the data-driven predictive control scheme, that this scheme is equivalent to the regularized approach that I showed you before to handle the presence of noise in the deterministic setting, when you choose lambda 1 equal to 0 and lambda 2 that tends to infinity. And this was actually a very useful observation, because as I told you, we didn't know how to tune such parameters. So since we know that this expression, this formulation of the problem is optimal within a stochastic setting, then we also have some guidelines on how to select a lambda 1 and lambda 2. We will see that actually in the asymptotic case, so when ND, the number of data, tends to infinity, this is the perfect choice. So if you take lambda 1 equal to 0 and lambda 2 that tends to infinity, you get very nice results. This is not the case let's say, in a general framework, for example, when you have a small number of data, because there is an additional effect that we have to take into account, and that I will tell you in a minute. But before that, I would like to improve this scheme a little bit more. So let's take the original database reformulation of the system dynamics, so the one that expresses the let's say, any trajectory of the system as a linear combination of the trajectories that you have in the data set. Well, actually, we could improve this by thinking that actually the problem of overfitting came out of the fact that alpha is very large. So the size of alpha is equal to the number of trajectories that you observe. So if the data, the size of the data set is large, alpha is also large, and this is why you need to regularize it. So we can do something to make it more efficient. For example, we could do LQ decomposition. And by doing LQ decomposition, we can prove that actually, in order to account for the initial condition, we just need to take gamma-1, so the new variable, as equal to L11 inverse times psi, so the initial condition. So the set of the new unknowns by taking the LQ decomposition is such that one unknown is devoted to the initial condition matching, and only the other, which is gamma-2, can be used in order to optimize the control and satisfying the constraint. So this is the final problem where you see you have gamma-1, which is gamma-1 star because we fixed it to optimize the constraint. So we have an analytical formula to find that. And the only unknown here is gamma-2, on which the sequence of the input, the optimal sequence of the input depends on. And this will have the same dimension of U. So we don't have an over-parameterized problem anymore. So we have two variables, gamma-1 and gamma-2, and these two actually have different objectives. And so if rho is suitably selected, we can use this formulation instead of the previous one, the one closer to the subspace predictive control, in order to solve data-driven predictive control within a stochastic setting. And this is just one example to show you how this works. So you see the benchmark example that was proposed in a paper by Berto Bemper a few years ago, and you see that the Monte Carlo simulation that we show, that the one in red, are very close to what you would obtain with an Oracle MPC. So the black line represents the result that you obtain when you use the exact model of the system. So we are very close, both in average and in terms of variance error. Okay, that these are 30 Monte Carlo simulations that show that they are close to the Oracle MPC. There is one additional ingredient. So I told you that with this new formulation, we shrink the number of optimization variables. And so maybe we don't need regularization anymore because we are not over-parameterizing our problem. This is also confirmed by the simulation, because if we introduce an additional penalty term, for example, this term that weights the norm of gamma-2, which is the actual optimization variable now. Here you see the attained versus Oracle cost, and you see that the best result you obtain for beta, and the same is for the input variable. So basically, the lower the beta, the more the closed loop behavior over 30 Monte Carlo simulation is similar to the one induced by the Oracle MPC. So that means that as far as the data is large enough, you don't need to regularize it, to add an additional regularization term to the formulation of the MPC. And the other interesting result is that if you compare our Gamma-DDPC, so this new formulation of data-driven predictive control within a stochastic setting, with other kind of MPC that are data-based, for example, a standard MPC, but that uses an identified model using, for example, an ARCS or an ARMAX model, well, you see that the performance are a bit better. And this is not because identification is not working properly. Of course, we could find an identification method that could work more properly. For example, we could select state space identification. We could take care of the process noise. We could do experiment design. So we could do something more. But if you just run the system identification toolbox with ARCS and ARMAX, you get, let's say, a bit worse results in terms of performance and input costs. And this is, let's say, motivating further research in the field in order to show when it might be the case to use data-driven predictive control rather than model-based, or the other way around. This is true only for large data sets. If you look at how the cost varies with the number of data, this is actually as expected. So we get worse as we decrease the number of data. And this has an effect also on the formulation, because actually if ND is low, so the number of data is too low, what we need to do is actually to add a regularization term. So we cannot get rid of it anymore. We can get rid of it if we have a large data set, but you will see, and we can actually prove it, that we need it in case of n large but not infinity. And the reason is that actually the prediction error that we would like to minimize in the loss is no longer zero. So it varies, it decreases with the 1 over nd, but it's no longer zero if nd is small. And then we need a term to counteract the effect of this noise. So one way, for example, is to add again a slack. So we add an additional sigma on the measurement of y in order to model the presence of noise, and then we try to push the norm of sigma down in order not to overfit the noise. But then, of course, we have some additional parameters to be tuned. In this case, we have lambda sigma. We also have the length of the path trajectory to formulate the terminal constraint, and we know that actually rho should be larger than n, but we could take n, so has to have a trade-off also in the choice of rho. We could also address the problem differently. For example, we could say, okay, since we know that the error is motivated by the fact that nd, the number of data, is small, then we can actually formulate or compute the variance of the prediction error using standard tools. And knowing this variance of the prediction error, we know how to design the corresponding regularization term. So in this case, beta 2 is has the role of trying to keep in the norm of gamma 2 small by setting the gamma 3 equal to 0, which was the third variable that they haven't mentioned so far, but that appears in the LQ decomposition. And the additional observation that we could make in this setting is that actually, since the variance of the error can be computed, we can also show that this is equivalent to this expression, which is, sorry, this is a typo that should be L. So the prediction horizon over n, so the number of data, times the norm of this two variables. So gamma 1 is given because it depends on the initial condition. And then we have gamma 2 of beta 2. And this notation of gamma star of beta 2 means that you have to take the best solution of beta 2 by just running several optimizations for beta 2. So we don't need, in order to tune beta 2, we don't need many closed loop experiments. We don't even need one closed loop experiment. We can just take this expression with the training data that we have. We run this different formulation for different beta 2, and we take the best gamma as the gamma corresponding to the beta 2 that provides the best performance. And this means that just via linear search, we could find the best selection for beta 2 with no closed loop experiment, just by starting from the expression of the variance of the prediction error. And you could do the same even if you keep gamma 3 into the picture. So if you don't set it to 0, you keep it into the picture, you want to regularize it, and using the same expression as before. So you know that the variance of the prediction error has a form like this. And so you can take, let's say, the best gamma 3 as the one corresponding to the beta 3 that gives you the best cost. And this is proven also in the benchmark example. If you look at the best beta 2 and beta 3, so in case of ND, number of data that tends to infinity, we know that we don't need regularization anymore. So all those efforts were useless. But if ND is small, in this case it's 250, then beta 2 and beta 3 are no longer 0 or infinity. So they are such that you need to weight carefully the norm of gamma 2 or gamma 3 in the two different formulations. And the interesting result is the plot on the right that shows actually the performance in case you regularize gamma 2 or gamma 3 compared to this cost bar. You say J bar 2 and J bar 3. This should be J bar 2, the second one. And this is the cost that you would get if you select beta 2 and beta 3 a posteriori. So by running several closed loop validation tests, so you select the regularization penalty and you use it. So this is a sort of oracle use of beta, and you see that the performance doesn't change with respect to the beta that is computed a priori using the expression of the variance of the prediction error. And this was a nice result to us, and rather surprising, because actually just by knowing the form of the error that we make by projecting the data onto the right subspace, then we can exploit this prior knowledge in order to shape and to design the regularization penalty suitably a priori, so with no unsafe closed loop validation test. So to conclude, there are existing approaches for the design of predictive controllers from data, but most of the results that we have found so far are in the deterministic setting with nice properties like recursive feasibility, exponential stability, but they just care about measurement noise only. And this measurement noise is usually assumed to be upper bounded in amplitude and deterministic in nature. So in order to move to the stochastic setting, we needed to go back to the origins, let's say, and reformulate the problem from scratch. So we started from the stochastic formulation of the MPC, and then we realized that actually just by rewriting the predictor using standard prediction techniques from subspace identification, you could end up with a formulation which is optimal in the sense of the minimization of the variance of the prediction error, and it's also corresponding to some results that were obtained 20 years ago in subspace predictive control, but within a constrained setting, so with some extensions. And starting from there, we could extend it a bit more by proposing this numerically efficient implementation that we call Gamma-DDPC, where the unknown is no longer the vector that expresses the linear combination of the data to find the future input and output. We take a decomposition of that in order to shrink the dimension of the unknown and have an efficient implementation that does not need to be regularized anymore. So in this formulation, we have gamma-1 that accounts for the initial condition fitting, and gamma-2 that takes into account the control design and the satisfaction of the constraints. The only regularization term that needs to be tuned and for which we need some selection and some initial test is the regularization due to the fact that ND can be small. So if ND is large, the number of data is large, we don't need that regularization anymore. We need it only if we had alpha into the picture. Otherwise, we need it only if ND is small and can be tuned actually offline. Some ongoing works regard the terminal ingredients. So even in this stochastic case, we would like to prove recursive feasibility and exponential stability. Of course, we would need different arguments because we don't have any bound on the noise amplitude anymore. And the other thing that we would like to study is this hyperparameter tuning in a more, let's say, precise way, not just using some guidelines with the asymptotic argument, maybe also looking at the case of small n, where you should provide a probabilistic and confidence bound. So thank you very much, and sorry again for the connection problems. I hope it went well at the end.
Thank you, Simone, for your nice presentation. So, well, we are perfectly on time. We have 15 minutes for discussion. So, so the floor is open for discussion. So, please take. So I see Guillaume has opened his mic. So.
Yes. Thank you. Thank you, Simone, for this presentation. It was great.
Thank you.
I've got a question. You pointed out the fact that there is a strong link between what you did at the end of this presentation and the subspace predictive control.
Yes.
So my question is, what is the advantage of using your approach if finally it's something equivalent to the SPC?
Well, it is actually SPC. So so the contribution of this work was actually just to establish a link between the two techniques. The only difference was that actually with the SPC, in the original formulation of SPC, you didn't have constraints. So it was just a receding horizon optimal control problem that was unconstrained. So we added constraints, and we showed that this is actually optimal also including constraints. And what we are currently working on is a proof of stability and recursive feasibility for that setting. The other thing that we have worked on is the role of regularization. So in the original subspace predictive control, there was no regularization. And actually, we proved that it's not needed if the size of the data set is large enough. But in case of small data, you need regularization. And that poses a problem on how to tune the penalty terms.
Okay. And so have you tested the SPC with constraints? So with the algorithm you want to add constraints, so CVX, for instance. Have you tested that and compared with your approach? And do you see differences in the results under simulation conditions, I mean, or not?
No, I would say that our approach is just a reformulation of the SPC. So it's nothing new. I'm not claiming it's something. It's not my contribution. So the contribution is just the connection between the two. And then once we know that the two are basically the same, then there is let's say another piece of research devoted to how to handle noise then when n is small, and how to make it efficient, let's say by reducing the number of optimization variables.
Okay, that's crystal clear. Thanks a lot.
Yeah, thank you very much.
Thanks, Guillaume. Any other questions? If there is nobody, I have one question, Simone. Thank you once again for your presentation. So if I have understood, somehow you need some initial data in your algorithm, and I think it's the data is called the UD and YD. And so, well, with this data, you could identify a model also. And so if I identify a model, then of course, I know that I would get a better model if I take more data. So a very long experiment, and if I take a U, which is large. Do you see the same phenomenon in your approach? That means that if your UD, you have a long sequence, that goes better. And now it is. How do I have to interpret that?
Yes, actually, it is. You can observe the same phenomenon, but then you also have, let's say, a different behavior of the data-driven control depending on the formulation that you take. For example, if you take the original data-driven predictive control formulation with the one that optimizes the alpha, so the linear combination of the past data, if you increase n, you are, let's say, you are considering more trajectories, and so you are capable of, let's say, averaging out the noise if you wish, but then you also have more unknowns, and so you're more prone to overfitting. So in that case, it's not you're not 100% sure that if you increase the data set you would get better results, but just because you have an ill-posed formulation. In this case, where you have basically cleaned up everything and you have projected your unknowns into the right subspace, then you observe the same phenomenon. Basically, because you have more information with the same amount of noise, and you have this sort of averaging effect inside the data set. Of course, this is the only the one in the slide is the only comparison that we have, but I wouldn't make any final statement about the comparison. Maybe I was not clear on this point, that I would like to stress it now. So I would never say that predictive control performs differently or better than.
It was just to see what I have to. Well, the only somehow design beside your regularization, maybe the only design I have, well, one of the design knob that I have, it's to choose UD, in fact. So I wanted just to know, you didn't claim anything. And so it's just to know, well, if I want to use your method, what do I have to choose for UD? So something, do I have to take a long one, hyper? And thank you for your answer. So it was just this sort of interrogation I had.
Yeah,
So-
well, I know that you've been working a lot on experiment design. That is also an open question in this field. So it would be interesting to see what would be, for example, the optimal experiment for this purpose in order to keep n small, even if you want to optimize the alpha, and so that you have a better posed problem, but still with the same amount of information, or maybe if you have a constraint into the input. So I've seen nothing in this.
Okay,
field.
thank you. That clarifies a lot your answer.
Thank you.
So I see Martin has opened his mic, yeah, and he has raised his hand. So Martin.
Hi, Martin.
Hi, Simone. Hi, Xavier. Thanks for organizing this, and thanks for a nice talk. So you discussed also the issue with the hyperparameters that need to be selected, or the regularization coefficients. But in a sense, there is another hyperparameter, which is your order of your controller to deal with. So how do you approach that part of the problem?
Order of the controller, what you mean? The length of the prediction horizon, or
so if you estimate a controller in this sense, well,
we estimate a sequence. So we suppose that you have 3 samples in the prediction horizon, then you estimate U1, U2, and U3.
Yeah,
in a non-parametric fashion.
And are there conditions on that prediction horizon such that you know that you can stabilize the system and so on?
Yeah, so this is a real tuning knob, because you know that with a certain prediction horizon, if you don't put any terminal cost, you could even lose stability. So this is why we put the terminal cost into the picture. Otherwise, I mean, you should choose the prediction horizon long enough, following model-based criteria in order to ensure stability, but these are not well formulated in a data-driven context. So one safe way to handle it is just to put a terminal constraint.
Okay.
And then you're free. Of course, the performance will depend on the choice of the prediction horizon. So you're right. I mean, if you take it too short or too long, you will have different performance, but at least from the stability point of view, you're safe.
And in terms of performance, can you predict beforehand how that will go, or is that really again a closed loop validation that you need to perform?
Well, yes, I would say maybe there is someone in the audience that knows MPC better than me, but in my personal experience, I couldn't say it. I mean, it's very application dependent, and it depends also on how you choose the prediction horizon, depending on the time constants of the system. So if you take it, too short, then you don't see any variation. If you take it too long, that depends on how fast it's sampled, so how the system is sampled, and how fast the system is.
Yeah, sure. Okay, no, thanks. That clarifies everything.
Thanks to you.
All right. Any other questions? No. Well, I have another question, because it was about your sigma parameter. So to encompass the noisy measurement, but it's much bigger. The first time you introduced it, where you had the alpha, in the formula with the alpha. Yeah, that one. So how do I have to interpret that sigma? Because and why do I want to make it small? So that's somehow why you put plus sigma there somehow? Because what does it represent, in fact, this sigma?
Well, this represents a sort of compensation for the presence of noise in Y. So suppose that Y could be written as the nominal Y, so the noiseless one plus some noise. Then by adding sigma, you're sort of trying to compensating the presence of this noise. And the problem is that if you do that and you leave sigma free, then you could mix up signals and noise, and you wouldn't understand anything. So you try to say, okay, I have some noise, but this noise is limited. And since I don't know any upper bound on the noise, I will try to put it as a soft constraint. So what you would like to have in an ideal setting is that sigma, the norm of sigma, is lower than a certain bound, but you don't have it. And so you put it as a soft constraint, so you lift it into the cost, and then you optimize with respect to lambda sigma, and this poses a problem of hyperparameter selection. But this is just, let's say, an intuition. So there's no theorem behind it.
Okay.
It's just an intuition to say we would like to model or to compensate the effect of noise on Y, and so we put this additional variable, and then we try to make this the norm of this variable as small as possible.
Yeah, because normally what you do is that you use the first equation with U bar, and you determine alpha with that, and then you apply the alpha to get the Y bar on the second part. Is that?
Yeah.
Okay. And so
this is an alternative formulation, and
yeah.
I mean the good side of this formulation is that this was the one that was used to prove robust stability.
Yeah.
So if you take the original paper, this one by Berberich and co-authors, that also won recently won the prize, I think the Axel prize. They prove exponential stability and recursive feasibility using this specific formulation, and that's why I put it here.
Yeah. And so because there is noise in YD, then the alpha is not representing well the thing, so it's not really allowing you to predict the Y. And so you say, well, the sigma is sort of bound on the error you made by having noise in YD. So
yeah.
Okay.
Yeah, this is it.
Okay, perfect. I get it. So I guess now we are getting to the point where we have to thank Simone for his nice presentation, his contribution to the meeting of today. So let's thank Simone.
Many thanks to you again.
I don't know,
Many
it's a
thanks to you.
applause sometimes. But thank you. So now we can switch to the next presentation, which will be given by Charles. So, and with from the Aerospace Institute ONERA here in France and in Toulouse. So Charles, you may share your screen.
Okay. Please, Xavier, if you can stop recording and restart it again.
Sure. Thank you.
Thanks.
Wait a minute. For that, I have to stop the sharing, I think. Share. Oh, yes.